Alright, this is Mr. Gilliam, and today we're going to learn about the geometric mean. And that's going to lead us into the altitude theorem and the lake theorem. Let's get started right away. It says the geometric mean is a special type of relationship between two ratios. Okay, you can find the geometric mean when you're comparing two numbers and their means are exactly the same. The means are exactly the same. So as you can see in this proportion, those mean numbers are exactly the same. All right, so the geometric mean between A and B is represented by whatever that number is that's going to make this proportion true. Okay. Now we've talked about solving proportions in the past. A fraction equals fraction. We cross multiply to solve. Well, if I take A times B, I have AB. When I take X times X, I have X squared. So the number that makes this ratio, this proportion true is called the geometric mean. So if I can find what that number is, then I know that's the geometric mean. And so what you'll find is the geometric mean between two numbers is the positive square root of their product. Okay, so we talked about proportions before. We talked about their extremes and their means. The extremes is the first diagonal here, the means are the second diagonal here. When the means are exactly the same number and the proportion is true, it's truly a proportion, that's called the geometric mean. Okay, and we're just touching on this now so that in a second we can apply what we know here about the geometric mean. Okay, so at the end of the day, this is the relationship of the geometric mean. Okay, that number that's the same on both of the mean values. If I wanted to find the geometric mean between 9 and 4, okay, I'll do it both ways. What it's saying is if I had this ratio this proportion comparing these two ratios where 9 and 4 were the extremes, the mean number, if it was the same, would be called the geometric mean. So I'm looking for that value that will make this proportion true, but it has to be the same number on both sides. Okay, it has to be the same value on the means. So if I cross multiply 36 equals x squared, and I take the square root, I know that x equals 6. Now because we're applying this to distances and things of that nature, geometry, there's nothing less than 0. Okay, there's no negative distances. We're going to use the geometric mean. There's the positive version. We don't need the negative version for what we're doing today, but keep in mind when you solve quadratics and you take the square root of both sides, there should be a positive and a negative version of the answer, or at least two answers. They might not be exactly opposite of one another, but there should be two solutions. In this case, I'm just going to keep the positive solution because we're going to talk about distances today. All right. On the last slide, we learned that, okay, well, if the means are the same, that's a geometric mean. Okay. However, we also learned that this is just a generalized formula version of the geometric mean. So I could have done the same problem and said, oh, well, the geometric mean was really just the square root of 9 times 4, or the square root of 36. So 6. So however you want to do it, doesn't matter. You can set up a ratio, proportion, and solve it that way, or you could do the little shortcut, the product of the extremes, square root of the product of the extremes. So again, we could do it again. Say x equals the square root of 8 times 10, square root of 80. Now I like to reduce them with the factor tree. And just a reminder on the factor tree here, it's almost like playing Go Fish. It's like for every pair you get to keep one of them. You get one pair, one match. So I get one match of 2s that goes outside the square root. I get another match outside the square root. And then the 5 is left inside the root. So in this case, the geometric mean between 8 and 10 would be 4 root 5. Okay, that would be the geometric mean. You could also set up a proportion because that's where the geometric mean comes from. It says, well, if the extremes are 8 and 10, my proportion, the means have to be the same for it, that value that will make this proportion true. If it's the same value for both means, that's called the geometric mean. So I could, of course, cross multiply and solve this as well and get the same answer. So however you want to think of it, it's important to know where this stuff comes from, which we decided is now 4 root 5, but you can generalize it like this way, or you can set up your ratio to find the geometric mean, as long as you kind of understand where it's coming from. It's the important part. Our first theorem here is the big one. It's a big deal. It's about a similarity. It has to do with altitude. So remember, an altitude connects a vertex to an opposite side with a 90-degree angle. So this first diagram here started as just ABC, this triangle. Okay, right triangle. It's very important to know that these are for right triangles. So this theorem is just specifically about right triangles. If I draw an altitude from the 90-degree angle to the hypotenuse, guaranteeing if it's an altitude that that will be a 90-degree angle, what I have is some triangle similarity here. I now no longer have just one triangle, but I have three triangles. I have the outside triangle, the triangle on the left, and the triangle on the right. Okay, and this theorem says that, well, if you draw the altitude from the 90-degree angle to the hypotenuse of the original triangle, those three triangles just so happen to be similar. Okay, we could go through this long developed proof about how they're similar and these types of things. But unfortunately, this is going to be a 15-minute video and we're going to have to squeeze it in already. So these three triangles will be similar, and their similarity statements, the order of the letters does matter. They're written for you here. And I know since we talked about similarity, we could all rotate these around and see which one's which. Remember, see in the similarity statements, the angle ADC and BDC and ACB should all correspond to their proper places in the similarity statement, because that's where all the 90-degree angles are. So if you look at your similarity statement, you know that the angles in each corresponding angle group on each similarity statement should be the same. So that's going to make sure that you have your letters in the correct order for your similarities. So I found this diagram that kind of shows what I'm trying to portray here. Once again, we're starting with this original big triangle here, and it just so happens to be a right triangle. And what happened was we drew an altitude from the 90-degree angle to the hypotenuse, guaranteeing, because it's an altitude, that it's a 90-degree angle. What happens is we're left with three similar triangles. We have the smallest, FJG. I'll outline him in pink. And then I have the second smallest, GJH. And I had the original starting triangle, FGH. And the nice thing about drawing little sketches of each triangle is that you can quickly tell what the similarity statement is going to be. So I can compare F, J, and G. Oops. And I know that's similar to triangle GJH, which is similar to triangle FGH. Okay. And so just seeing which triangles are similar is going to be important, because now we're going to kind of apply the geometric mean to what we just learned. So look at this next diagram here. Once again, I'm starting with this triangle, this big triangle, and it was a right triangle indicated by this right angle, and I drew an altitude to its hypotenuse. Now when I say altitude, I mean that guarantees me that I have a right angle where they intersect at. So if these are my similarities, my three triangles right here, I don't necessarily need a similarity statement right now because I'm more particular about the diagram. I can make some comparisons. Now, I want everybody to be very clear on this. We know for a fact that these triangles are similar. Okay, so if I compare, when we talked about similarity and proportionality and that type of thing in a previous chapter, I said, okay, well, make sure that you're comparing one triangle to the other and one triangle to the other, like that, like so on and so on. Don't compare two legs of the same triangle to two legs of the other. And the reason I said that was because we don't know that they were proportional. When we were learning that stuff, we weren't sure if they were proportional or not. Okay, so we couldn't guarantee that that relationship was a true relationship. But now this theorem promises us, yes, these are proportional relationships. Okay, these triangles are proportional. And so some of you are confused and say, oh, well, I got the same answer, Mr. Gillum, how could that be? That's true. If they are proportional, the ratio of their side lengths, or I should say their leg lengths, will be the same ratio in all of them, as well as their ratio from a leg to the hypotenuse, or so on or so on. However, when we were doing that chapter, we didn't know they were proportional. We were checking to see if they were proportional, or we were looking for a value that would make them proportional. Hopefully that all made sense. Today, we're going to compare, since these are all proportional, their side lengths all, each ratio of their side lengths and that type of thing are all going to be equal. So I first want to compare short leg to long leg. It's like my short leg to long leg, my B to A, my X to H, and my H to Y. B to A, X to H, H to Y. I also want to have a comparison between the hypotenuse and the shorter leg. So I could also compare C to B, B to X, and A to H. Okay. Also, I could compare. Another comparison would be we could do the hypotenuse to the other leg. C to A, B to H, and A to Y. And I just want to reiterate that these three triangles came from when I made the altitude from the hypotenuse to the from the 90-degree angle to the hypotenuse. These three triangles kind of drawn out so you can see each one individually and you can compare the side lengths easily. But the relationship that I want you to see here is the one that's circled. All right. If you notice here, something crazy happens. These comparisons, their means are the same. Okay, their means are the same. That means what we have here is geometric means. So instead of having to do all these rules we learned about similarity, now we can use the geometric mean to help us solve for some of these missing parts quicker and actually with less information knowing this relationship. The altitude theorem is the first theorem I want to talk about today, and it says if you draw that altitude on a right triangle from its 90-degree angle to its opposite side, then this altitude length is actually just the geometric mean between x and y. So for instance, if I said that x was 4 and y was 5, then I know that h would actually be the geometric mean. H would equal the square root of 4 times 5, or the square root of 20, or if you did a factor tree, you would know that's the square root of 5, 2 square roots of 5. Okay, so I know that this length would be 2 root 5. So we're going to apply this geometric mean to similarity of triangles. Okay, but specifically, it has to be right triangles. Okay, the altitude has to go from a right angle to the hypotenuse of the original triangle. Then we know that the geometric mean between the two sides that the altitude is splitting is the length of the altitude. Okay, it's called the altitude theorem. We also have what's called the leg theorem. And the leg theorem is the tricky one. Okay, we have this right triangle that we started with, and we drew the altitude from the right angle to the opposite side. What it does is it compares the hypotenuse to the leg. Okay, so I could set up some ratios that C is compared to B, and if I'm looking at this triangle here, B, which is now the hypotenuse of this little triangle, compared to X. Okay, so what it's saying is I can find the geometric mean of C and X, and that will be representing the length B. Okay, so the geometric mean of C and X equals B. And that goes for the other triangle as well. C and Y, its geometric mean will equal A. So the geometric mean of C and Y equals A. Okay? And this was all illustrated earlier when we separated each of those triangles and we found their similar parts. All right? So the two theorems I want to talk about, the altitude theorem, where the geometric mean of x and y equals the length of the altitude, and the leg theorem, the geometric mean of the original hypotenuse compared to its leg, hypotenuse compared to leg. So the geometric mean of C and X equals B, geometric mean of C and Y equals A. We're going to have just enough time for one example here to apply what we know. If you need to pause the video if I'm going too fast, please do that. I want to make this longer than 15 minutes. I need to find what X, Y, and Z are, and I see that I started with the right triangle, and I made its altitude, guaranteeing me a right angle there. The first variable to find would be X. I know X would be the geometric mean between 20 and 5. So the square root of 20 times 5 is the square root of 100. X must equal 10. It's a good start. I also know that this entire length is 25. So the geometric mean between 25 and 20 would equal Z. And for the sake of time, I would know that the geometric mean between 25 and 5 would equal y.